Hello, welcome back to the video tutorial series for Mr. Billingham's AP Calculus BC class during the COVID pandemic and shelter at home. So in this chapter we'll get into the material that has been specifically excluded from the AP this year, but those of you who are just interested or know you're going to be going on in math would probably benefit well from working on this. Also, as a special treat, we have memes. These are courtesy of Michael Kaufman, Luke Arambidi, Brian Brown, and Marshall Mann, and I have 6 of them. I really enjoy them, and I hope you will too. And because I'm going to be doing 3 video tutorials for Chapter 11, we're going to get 2 in each. So let's start off with our first meme. I didn't realize Baby Yoda was in the class. I guess he must have been hiding. Anyway, hope you enjoy this as much as I do. And now on to the material at hand. In 11.1, which has to do with the calculus of parametric functions, we're first going to review the topic of parametric functions. We'll look at how to calculate first and second derivatives, which we actually did earlier in the year. And finally, we'll go over the formula for curve length in parametric equations and work some examples. So here we go. In this problem, just to practice and review parametric curves, we're going to sketch these graphs, and we're going to then eliminate the parameter to find an equation relating x and y directly. So in A, we have x equals cos t and y equals sine t in the interval 0 to 2 pi. And when you're first starting out, it really can help to make a nice little table. You want to include t. So I'm going to do t at 0, pi over 2, pi, 3 pi over 2, and 2 pi. X cosine of 0 is 1, cosine of pi over 2 is 0, cosine of 3 pi over 2 is negative 1. Cosine of pi is negative 1, cosine of 3 pi over 2 is 0, and cosine of 2 is back to 1. Sine, of course, goes through the same numbers, but it phase shift. So sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1, and 2 pi are back to 0. So basically, we start at 1, 0, go to 0, 1, negative 1, 0, 0, negative 1, and back to 1, 0, making a familiar circle. To eliminate the parameters, pretty easy. We just square. So we get x squared is cosine squared of t. Y squared is sine squared t. If we add the two together, you get x squared plus y squared equals 1. A familiar unit circle. All right. Second one's very similar, except now x is 3 cos t and y is 2 sine t. So that means x can get as large as positive 3 or negative 3, and y can get as large as positive 2 or negative 2. I won't go through a lot of detail, but this is going to stretch in the x direction, and this is an ellipse. And if we divide the first equation by 3, the second equation by 2, just like we did before, we square them and add, we'll get x over 3 squared plus y over 2 squared is, and cosine squared t equals sine squared t is 1. So there's our second one. The third one, I'm going to eliminate the parameter by squaring x. But remember, x is just the principal root of t, so x can only be positive. I'll make a little table first to help us figure this out. So you'll notice the first point is at 0, negative 2. From there we proceed to 1, negative 1, and then to about 1.40. about 1.71 and 2.2. So the curve definitely has a sense of a beginning and an end, and it looks like part of a parabola, which in fact it is. Let's look at the math for eliminating the parameter. So there are three examples of sketching parametric curves and eliminating the parameter. Now let's talk about how to find the derivative dy dx in parametric form. So here's the way that I think about parametric derivatives. So the idea is, of course, that y is a function of t and x is a function of t. But these are really two-way streets. If I modify t, then both x and y change, but if I were, for instance, to change x a little bit, that would cause t to change and that would cause y to change. So pretty clearly, y is connected to x. How about if I do a chain rule dy dt by going the long way? So dy dt would, by the chain rule, be dy dx times dx dt. And if I solve this for dy dx, I get dy dx is dy dt divided by dx dt. Now, in this, y can be any function at all of t, and typically dy dx is a function of t. So take this formula and substitute dy dx in for y. When I do that, I get the following. So this gives me the formula for the second derivative parametrically, because the first expression is d squared y dx squared, and the second expression is derivative with respect to t of dy dx divided by another dx dt. So let's look at that. So the two formulas to remember here are to find dy dx, you just take dy dt and dx dt and divide them, and to take the second derivative of y with respect to x, take that first derivative you just calculated, differentiate it with respect to t, and divide by another dx dt. Here's a nice example. You could probably do the graph manually, very slowly and carefully, by approximating fractions of pi squared and things like that, but I think this would be a problem that was on the calculator part. So you would need to know how to do graphing in parametric form, and that's just very simple. You change your mode to parametric mode, and you enter x1 of t and y1 of t, and the t min and t max. It's pretty simple, but you'd get a graph that looks a lot like this. The next question is interesting. Find the highest point on the curve. Well, the only value we need to worry about is y of t. And to maximize y of t, we just want to take its first derivative and then use one of the two tests for determining that it's a max. Here's the work in doing that. So I went ahead and did the first derivative and got y prime of t is 2 cos t, and that's equal to 0 when t is pi over 2. That's a critical point. I'm going to use the second derivative test just to remind you about it. The second derivative of 2 sine t is negative 2 sine t, and at my critical point that's negative 2, which indicates downward curvature. So let's find the coordinates of that highest point. Again, presuming this is a calculator problem, we could substitute those values into our calculator and get the following. In the last part of the question, they want us to get points of inflection on the curve. So we're going to have to find second derivative of y with respect to x. So I'm going to go through the steps here. So at this point, I have to get the derivative of dy dx, which is cos t over t, with respect to t. So remember our chain rule? So low d high minus high d low over low squared. And then I have to divide that whole thing by another dx dt, and dx dt was 2t. So there is our formula for the second derivative. So if I take that and graph that on a calculator, I will find the t value that makes that expression change sign. And that turns out from a graph to be about the following. Remember, this is a calculator test, so store that answer in your calculator and then plug that into each of x of t and y of t, and you'll find the point of inflection is approximate. So that concludes how to take the first and second derivatives. And although we did that earlier in the year, that's worth remembering for the future, although it will supposedly not be on this year's AP test at all. So let's move ahead. Can you think back to when we figured out the formulas for arc length? I'll bring it in a diagram, so we'll take a quick look at it. The idea involved the big key idea that differentiability implies local linearity. So the segment from P to Q is approximately linear, and if I wanted to calculate its shape or its length, I could use the Pythagorean theorem. So it's the sort of the hypotenuse of a right triangle, and its length would be the square root of delta x squared plus delta y squared. And if I did that for numerous little segments along the path, I could approximate it. And the way I can make this easier is divide internally by delta t squared and multiply outside by delta t. So this becomes delta x over delta t squared plus delta y over delta t squared times delta t. And if I take the limit as t approaches infinity, I get this formula. And that's the formula for parametric arc length. You go between the parameters t equals t1 and t2. I'll work an example in a minute, but first I wanted to write out the other two formulas for curve length. I hope this jogs your memory. So those are the three formulas for curve length, one parametric, one in terms of dy dx, and one in terms of dx dy. So no big new thing here. So there's the formula summarized a little more neatly. Let's work an example. So first we're going to need to calculate dx dt and dy dt. So there I've gone ahead and used the chain rule and calculated dy dt and dx dt, and I've squared them both. Now when I add those two together, I can factor out a cosine squared t and a sine squared t as follows. And of course we know that cos squared t plus sine squared t is 1. And so my expression becomes so the length of the curve would be Anyway, I could do this integral a couple of different ways. I could let u be sine t, and then du would be cos t dt, so I'll wind up with 2 times sine squared t over 2 from 0 to 2 pi, whole thing times 3. I could do it that way, or I could recognize that sine t times cos t is half of 2 sine t cos t, so this could be 3 halves the integral of sine 2t, which is also an easy way to do it. Anyway, you get the length of the first quadrant thing comes out to 6, if you want to check the math. All right, next we're into cycloids. Suppose I put a spot of bright white paint on the wheel or the tire of a bicycle wheel, and I slowly rolled the wheel along the ground. If I trace the curve in space that the little dot of white paint took, that's called a cycloid. Here's a little illustration to help you think about it. And here's our first challenge. We're asked to write parametric equations for the cycloid. And to do this, we'll imagine that that point P, which is our spot of paint, starts at the origin and that the wheel is moving right. In my mind, calculating the x-coordinate is a little bit like you're on a moving escalator at the airport, you know, one of those moving walkways, and you have a little child with you who's hyperactive and he's running forwards and backwards and forwards and backwards. So there would always be a component of the x direction that was equal to AT, but also it's going to be moving, as you think about it, left and right of the center according to the following. Relative to the axle, as the wheel's turning, that point P is going to be, first of all, 0 to the axle, then -1, then 0, then 1, as the point moves round and round and round. So again, to illustrate, relative to the wheel, the point starts here, 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 and repeats. So in other words, I'm going 0, -1, 0, 1. And if you think about that, that is negative sign. Meanwhile, the y value relative to the axle, which is at 1, starts at -1, then it's 0, then it's +1, then it's 0. So the y value is pretty simply, that's way more than you'd ever need to know about cycloids, but let's go ahead and calculate the length of one arch of the cycloid. First, I'll calculate dx dt, and now I'll calculate dy dt. If you add dx dt squared and dy dt squared, you'll notice that you'll have a squared cos squared t plus a squared sine squared t, which you're going to add together to be an a squared. And so you'll wind up with 2 minus 2 cos t whole thing times a. So the curve length will be, and assuming this is a calculator problem, you could do this with numerical integration, and the answer you get is 8a. Anyway, I think it's time for our last meme. Here it is. Thanks for the memes again go to Michael Kaufman, Luke Arambidi, Ryan Brown, and Marshall Mann. Anyway, stay healthy. The next installment of this is going to be the calculus of polar functions. Again, the topics in Chapter 11 are not on the AP Calculus exam this year, but those of you who want to go on in math or are just interested are encouraged to watch them. All right, bye-bye. Stay well.